Section 1.13 deals with average rates of change again. So we were introduced to it a few classes ago, but now we're going to kind of take a deeper look into what it really means for us. Well, what I'm looking at right now is a graph, and we're going to call this our function p. And our function p here is dealing with the position of a particle at any time t. Okay? And we're going to say t is in seconds. So don't get overwhelmed by that. It's pretty much just telling us that if we want to find our particle, then you just need to tell me what time it is, and I'll tell you where it is. Right? So, like at time 2, I seem to be at position 2. At time 3, I'm at position about -1. So, when we're looking for average rates of change, right? The average rate of the change of position. That's when we're talking about the slope between two different places. So, for example, let's take a look at time 0. Okay? So at time 0, we have our height, or our particle is at position 2. So this would be easy for us to say, well, P of 0 equals 2. Well, and then if we also look, let's say, at another place. So P of 2 seems to also equal 2. So when we were to look at an average rate of change of this, the average rate of change is going to always look in the following way, right? We take the difference in our y values, which is nothing here. So we get P of 2 minus P of 0. We divide that by 2 minus 0, which, again, this is 2 minus 2 over 2, which, again, is just nothing. Well, this 0 means something very specific. It means that if we were to draw what is called a secant line, so a secant line is a line that connects two places on a curve, and it can go through them. So our secant line here has a slope that is 0, because over the entire period from 0 to 2, regardless of what's happening, since they end up at the same position, there is no change of position. There's no change of position at all. Now we can see that this graph moves, right? It dips down and then comes back up. However, on average, it doesn't do anything. One thing that is important to point out, that the change of position over a change in time, this is equal to what's called velocity, right? And so now if we're looking at average change of position, we want to throw in the average. That's average velocity. Okay, so if you think about it, if we look at over this period of time, we would thought, on average, it hasn't moved or it hasn't done anything. Well, it has actually done stuff, right? It starts off, it kind of is going down, and then it surges back up. So we can only really tell this average over the whole period. But we can see graphically what's going on before then. The velocity at first here seems to be negative. See, this is a negative velocity, right? Because the slope here seems to be negative. Then it kind of rebounds and it becomes positive. Only again to go through the process of going through negative and positive again. So when the act of us gaining position over time means that we have a positive velocity. The act of losing that position over time is a negative velocity. And so visually in the graph, we can see when the graph is speeding up and slowing down, right? We can see when we can see when it's moving forward and moving backward. And we can also tell when it's not moving forward or backward. Right? The places on this graph where we're not moving forward or backward are these kind of choke points, right? They kind of stop because there is no slope at these places. So that is an important thing to realize here. Now, if we would like to make a line, like talking about, we made our secant line earlier between here and here. All we need is a point and a line. So just remember, we have our trusty formula that's y minus y1 equals m times x minus x1. So if we work with this, you'll be able to do quite well with that. So just make sure that if you need to make a line, that's how you're going to make it.